comparison of analytical and numerical solutions. Our mentor is Mohammed Amin Kotkar, primary investigator, Professor Mayberg. I'm Miguel Toledo.
My name is Ray Fernandez.
I'm Jeffrey Johnson.
And I'm Summer Estes.
So first, we want to begin by defining what a gravity current is. A gravity current is a wavefront caused by differences in fluid densities. We are going to show you a video to demonstrate what a gravity current looks like. So in this video, the green fluid is called the gravity current, and it's more dense compared to the blue fluid, which is called the ambient. And this small differences in densities causes the green fluid to have a horizontal flow to your right. So why do we study gravity current? We study gravity current because it can be applied to different industries that we rely on today. For example, by understanding certain properties of gravity current, we can determine where wind gravity current are going. As we can strategically relocate and build where wind turbines can be built to maximize energy efficiency. In terms of finding oil deposits, ocean gravity current on the seafloor are capable of transporting materials such as fossil fuel from point A to point B, much like tornadoes transport debris from point A to point B.
So this is another example of a gravity current. The sandstorm here has picked up all the sand, causing this here to become more dense than the ambient out here. This difference in density is, again, what drives this motion of this sandstorm. What we want to do is we want to take this large, messy, complex system and get this. Our goal is to develop a mathematical model that allows us to simplify the system, and in the end, the property we're most interested in is predicting its velocity. So the blue shape here represents like the gravity current, the sandstorm. This white area is then the ambient. And importantly, the gravity current is more dense than the ambient. This is the height of the gravity current, and this is then the height of the channel. What that means is that this is basically the height of the fluid, the ambient out here, right? That is influenced by the motion of this gravity current as it's traveling. So in order to make this problem easier to solve, we employed a strategy. What we did is we changed reference frames. So what that means is instead of being like a bystander watching our sandstorm go by, we're pretending that we're riding on top of this gravity current, watching the ambient flow past us. This is similar to how like you get in your car and you're driving, and you feel like you're sitting still while all the scenery is rushing past you. So again, our velocity was originally our gravity current. We changed reference frames, so now the inlet velocity is over here. It's the velocity of our gravity current, and the outlet velocity over here. Additionally, we found we needed to incorporate the height of the exit channel. And while we were solving, we found that we needed to incorporate pressure in our model, which you can see over here.
After defining parts of our system, we identified what we don't know and what we do know. We know all the heights of our system and the densities of the two fluids. What we don't know includes the velocity of our gravity current, UG, the velocity of the outlet, UO, and the pressure inlet and the pressure outlet, its difference, which is called pressure drop, and head loss, which is shown with a delta sign. Head loss is a very complicated variable, so we are going to cover that on later slides.
So once we have defined our knowns and unknowns, we can begin to build a mathematical model. Using fundamental laws of physics, such as law of conservation of mass, conservation of momentum, conservation of circulation, and conservation of energy, we're able to come up with 4 equations to solve for our 4 unknowns. Due to the inherent complexity of these equations, We cannot go into proving them as it would take too long. However, we can see here our 4 unknowns are incorporated in the 4 equations. We have the velocity of our gravity current, our pressure drop, velocity of our outlet, and head loss. Head loss is a term used to describe energy lost due to friction and mixing of fluids.
Okay, who likes to work with really large numbers and calculations? Well, you're crazy. We like to keep it simple here, so we use something called non-dimensionalizing, where we take our unknown variable and we divide it by a known variable with a similar unit to cancel out the units and make them essentially unitless, so that it's easier for us to scale down values in our mathematical models. We then put our mathematical models into a computational program called Matlab, and it compiled our data into nice, neat little graphs. And the graph on the left represents the correlation between the gravity current velocity and the height of the gravity current. Our graph on the right has our head loss on the y-axis, and then the height of the gravity current on the x-axis. Now, head loss again is the energy lost through friction and mixing, and it's important to know that it must always be positive. It cannot be negative. Negative energy means that you are gaining energy from something that isn't there. So we discovered that we must have a height of gravity current of 0.5 or less in order to keep the head loss positive.
Once we have understood the correlation between head loss and the height of the gravity current, we can begin to compare our model to computer simulations. Using a computer simulation is preferred over experiment because it is more cost efficient and can be easily replicated. The computer simulation that we're using here was developed at UC Santa Barbara at the Computational Fluid Dynamics lab. So to test the accuracy of our model, we measured the deviation of our predicted velocity to the velocity computed by the simulation. Keep in mind that these simulations are in reference to the gravity current. This means that if our model is accurate, we can expect the gravity current to appear nearly stationary. So we can draw your attention over here. As you can see, there's not much motion going on, and it remains nearly in the same spot. At a height of 50%, the model is accurate, which corresponds to a head loss of 0. The simulation serves as an excellent benchmark when predicting a 0 head loss. However, it becomes problematic when our models begin to predict a head loss other than 0. For example, at a height of 75%, our head loss corresponds to a negative head loss, which means the energy is being gained. And at a height below 50%, such as 41%, which is an arbitrary term picked, we predict a positive head loss, which means energy is being lost. By playing these two simulations, we can notice that the great displacement in our simulations resulting in a higher percent error.
So we found that our model, our mathematical model we developed, is accurate, it's highly accurate, but in certain situations. Most importantly, it closely agrees with the simulation that we were using when head loss is 0, which, due to previous work, and here in the Computational Fluid Dynamics lab, we found that simulation is most accurate when we assume that energy is conserved when head loss is 0. However, because our model is incorporating head loss, whereas the simulation does not, the results where our model does not agree with the simulation is inconclusive. We're not sure whether the model is correct or the simulation is correct. So further testing is needed on that front. So again, the previous work in this field has assumed that energy is conserved throughout the system. The novel approach that we used was to incorporate this head loss term. So today, this model is actually being, the work published by our mentor, it is actually being used in other labs around the world. For example, in the University of Melbourne in Australia, University of Cambridge, UC Davis. It's being applied on problems involving naturally occurring gravity currents. Additionally, further research is being conducted here in UC Santa Barbara, applying the model to various other geometrical problems. So in the future, what we would like to do is to test our model against physical experiments in order to determine how accurate it is in those non-zero head loss situations. Additionally, we could potentially improve the simulation to incorporate the head loss, and in order to determine again which model is more accurate.
And we'd also like to give thanks to being invited to Jack Kent Cooke Foundation, our wonderful coordinators, Jens and Maria, for putting everything together, our mentor, Amin, and our PI, Professor Nathan. Also, our RAs were wonderful. Jordan really helped us a lot. Thank you. Are there any questions? Sorry.